Okay, good afternoon. The example that we mentioned in the previous, this was the example. The method that we analyzed this example is say it is first of all it's a tree diagram. Uh, it's a tree. We say that we have different types of the water distribution networks. We have a tree. This is the tree system. The tree system, it means that you have a line, then there will be another line, and there will be another line, and so on. It looks like a tree. And the method is we have Q1, Q2, for example, Q3. Now, in this junction or in this node, the Q1 will equal to Q2 plus Q3. And in this junction, if I have Q4, for example, and Q5, so Q3 is equal to Q4 plus Q5, and so on. This is called continuity equation. Now, this was one of the systems that we said, and the method that we are using to analyze this kind of system is by, first of all, we will have the Q for this pipe, which was 220,000 liters per minute. And we have to find its meter cube per second. We have the Q here, and we have the length. And by the way, we have the ground level of A, point A. Ground level of point A, it means that there is a tank at point A, which is 20 meters above this one. This is the ground level, I mean by the level of water at this point. If this was 20 meters, so by gravity, the water is coming to this point, right? And the level of point A is at 0, and the level of B is at 0, and all the levels are in the same level. This is given by the question. So what that means, that we have the pressure here at point A is 20 millimeter, and the flow will come from this point to point B. And the Q in this point is 20,000 liters per minute. So what will be happen? There will be a head loss in this pipe. This head loss can be found by using either William Hazen equation or Darcy-Weisbach equation. And remember that in the previous chapter I said that there is a problem with this number 4. Yeah. This is Darcy-Weisbach equation. The Darcy-Weisbach equation, we have F, and we have F sub D, and this is called Thomas passing friction factor. So the relation between these two frictions is 4. So this is the William Hazen friction factor, or Moody diagram friction factor. This is what I told you, that we can find this F from the Moody diagram. We have the friction here, and we have Reynolds number here, and we have the E over D for the pipes, and we have laminar flow till 2000. From 2000 to from above 4000, we have turbulent flow. So we can find the E over D for the pipe diameters and the roughness of the pipe diameter of the pipe, and it will give you a relative roughness. And the Reynolds number is, as we take it in the fluid, is equal to rho Vt over mu. Then from these two ones, we can get the value of F. So this is for this is called Darcy-Weisbach equation, and it will be equal to 4 of the another friction factor, which is not longer taken as from for the fluid. It's only the well-known one, which is the Darcy-Weisbach. Now we say that we can use this equation, or we can use William Hazen equation to for William Hazen equation. for finding the head loss. What I should do with that head loss, I will use it for finding the head loss at point B. Remember that. Again, here's the, and this was the question. What we did, we have pipe AB. Here's the pipe AB. The length for the pipe AB was 400 meter. Here's the 400 meter. From A to B was 400 meters. We have the Q in that pipe is 20,000 meter cube liter per second, which is equal to 0.33 meter cube per second. After that, we will there will be an assumption for the diameter, and there will be check, and we assume that this is a 20-inch pipe diameter. This is will be 540 millimeter, and converting, you have to find the area of this pipe. How much it will be the area? It will be 0.2074 meters square, and we will find the velocity through the dividing the Q by the area. It will give you the velocity. We said this velocity should be within a specific range, and this range again, it's between 0.6 to 1.5 meter per second. Why it's 0.6? Not should be in the 7.6. We don't need to for the sedimentation to occur in the pipe, and we don't need to have a high velocity in the pipe because of the turbulence flow. Then after that, we will consider the equation which is asking for we say the Darcy-Weisbach equation, FL over D, P square over 2G. The L is given, the diameter is given, the velocity is, we have it. So just we have to use that F, and we can say this F can be founded by the Manning, the Muti diagram, and we say this is one. Now, the head loss is 16.4. Before that, we should add another column here. This another column is to find what is the value of S it will be. The value of S here, we said S is the head loss divided by the head loss
by the length of the pipe.
Yeah, so means 16.4 divided by the length of the pipe, which is 400, and which is equal to how much we see?
4.1 was it? I believe 4.1%.
4.4%, right?
Doctor,
Yes.
the head loss was 16.04, not 16.4.
16.04.
Yeah.
So 16.04 divided by 400, it will give you about 4.01%, means 4%, which is okay. Now, this will be the pressure at A now is equal to 20 meter, right? This is given by the network. It said that in point A we have a level, the ground level of A. We have a tank. A tank is above the ground level by 20 meters, so it means the level of water at point A is 20 meters. Now for point B, pressure at B is equal to pressure at A minus pressure at B, right? Minus the head loss that we have from A to B, which means 20 minus 16.4, which means how much? 16.0, sorry, which means 4 meters. Now, we have the pressure at B is 4 meters. Now, I will go with the second part of the pipe, which is, here's the second part. So we have now the pressure at B is 4 meters. I want to see how much it will be the pressure head loss to the B to B prime. So BB prime, we have the length of the B to B prime as equal to how much? B prime, we have the length is 200 meter and the flow is 4,500. So we have 200 meter length and we have the Q for BB prime is equal to 4,500 liter per minute, right? Again, so we have from B part, we have 200, we have the 4,500, and this is should be converted to meter cube per second. So 4.5 meter cube per minute divided by 16. Yeah, 4. It will be 0.075. This is will be meter cube per second. And we will assume another diameter for this part, and we will check that one later. Now,
Sir,
yes,
I have a question regarding the assumption.
yes.
Like, okay, for example, we assumed the first number, which was like 514. The second number, like by how much should I increase the volume? Is there like a specific range, or I just keep
It's
assuming?
just, yeah, just will depend on your experience. This is the assumption, but literally it should be less than the main pipe. It's a
Okay.
lateral pipe, okay? So it will depend on your experience. By the way, there is another methods I will let you know how to assume the diameters. This is will be based on the knowledge and the demand of the water. There is a method, it's called section method. It will help you to at least, let me show it to you. We have the methods that we are using them to design. We have 4 methods. Yeah, these are the 4 methods that we are using them for the design. We are using an equivalent pipe method. That is for a limited number of the pipes. We have a method of sections. This will help you to at least have an idea about about the pipe diameters. And what is the method of sections? You have the master plan of the city. You have the, let me see, this is the master plan of the city. And okay, like this. And you have the pipes coming from this way and this way and this way, this way, this way and this way, yes, this way and this way. So what you're gonna do, first of all, you will take a section like this, section 1, 1. And for this section, you have the this people here and people here, and then because it's a lateral, you will find the Q5 for them for the flow for this area, and you will assume the diameter. You will find the diameter based on this Q. Or how this will be? You will assume a velocity at, for example, 1 meter per second, and you have the Q fire. So from the Q and V, you will find the diameter. This diameter is initial diameter. This is a predicted one. You will put it in this way. In the section 2, here's section 2, is to define or is to find this diameter. Or this diameter, you will include every section, you will include another area added to the previous one. This method just help you just for prediction, initial prediction, primary prediction for the diameters. That should be checked later. Okay.
Okay, thank you, doctor.
Hello. And back to what we said, we have the length, we have the flow, and we assume that the diameter here should be BB prime. We assume that it will be half of, for example, it's 10 inch. So 10 inch is about 262 millimeter. The 10 inch here is 262 millimeters diameters, means about 10 inch. So I have the diameter again here, and I will use the same F as we said, it's 0.4. And we will use the FHL as we have it in the equations. By the way, you can both an Excel sheet file for such kind of design or such kind of analysis. So 262 was the millimeters, it was the diameter. Now what will be the area of the 262? It's pi d squared over 4. So pi it's 13.4 times 0.262 squared divided by 4. It will be
0.0538.
good. 538, or say 538. This is meter square, right?
Yes.
Now, again, after that, we have to find the velocity. Now we have the Q. How much is the Q? It's 0.075. 0.075 is meter cube per second. And we have the area of this pipe, which is 0.0538 meters squared. Now I will get the velocity in this pipe. 0.075 divided by 0.0538. It will become as equal to 1.39, which is okay, meter per second, and that's because I have a little bit experience for putting the diameters. Now after that, what should I do? I should find the head loss. The head loss here is again it's the we have to find this HL. We say the head loss is equal to FL over D V squared over 2G, and it's equal to, we say the F is 0.04 times the L is the length of the pipe from VB bar, which is equal to it's equal to 200 meters. So I should be to here.
Doctor, why in the first we use the 4 in the equation and for this one we are not using it? Isn't that changing the answers a little bit? Or should we change the first one back to this one?
Yeah. Did we use the 4 here in this equation?
Yes, we used it.
So
if we don't use it, it would be 4.
Yeah, so that was wrong. I think it will be divided by 4. It will be 4. 16
Yes.
will become 4. So that's, thank you. So
Okay.
this will be 4. It will be 4. And then the 4 divided by 400 will become half much. So about 1%, right? Am I right? So
Yes,
4 by
doctor.
is 1%. And then the 1%, we have the pressure at A is 20. So the pressure at B will become how much?
19 in this case.
Yeah.
Yep.
I'm sorry about that. I think we made a mistake. So it will become 19. Now, sorry, it will be 1 meter. 1%, the head loss now we have it 4 divided by 400 is 1%. The head loss it's 4, right? 20 minus 4 is 16. So the pressure at B is now 60 as 40. Yeah, this is the pressure at B is 60. So the head loss is 1. The head loss is 1, which is accepted because we need to have an S should be between 1 to 3. This is the design requirements by this way. Now for the second pipe, we said we have to find the L. We say the length is
200 meters.
So F is 0.04. This is the Moody diagram times the L. We said it's 200 meter. The diameter is 0.262, and the velocity is 1.39. This should be squared divided by 2 times 9.81. Now, what will be the head loss here in this case? It's 0.04 times 200 times 1.39 squared. That's 15.4.
3 meters.
Sorry, yeah, correct. This is will become 3 meters. So the head loss from B to B bar, let me show it to you. So from this point to that point, we have a head loss, which is 3 meters. Now 3 meter head loss from that one to this one. Now let me check on this tree, if I want to see how much it will become. This is the head loss. So the pressure at point B was 16 meters, right? And from B to B bar, we have a head loss will be as value of the head loss is 3 meters. So what will be the residual pressure at this one? It will be
13.
16 minus 3.
13.
Okay, we have 13 meters, which is 1.3 bar, which is okay. We have for the municipalities, we say that should be more than 1 bar. So the pressure at this point, it will be 1.3 or bar or 30 meter. Now let's check the value of S. We have the head loss is 3 meter, right? So 3 divided by the length of the pipe, which is 200, it will become 1.5%, which is also okay because it's between 1 to 3. Okay. When you are you have to just analyze or check a distribution network, you have to do these points. Now we say this is 3, and 3 divided by 200 will become 1.5%, and the pressure at B bar is equal to 16 minus 3, which is equal to 13 meters. Now, in this way, you have to go again for the next pipe. And where is the next pipe? It's VC. B and C, and you have to do the all values as we mentioned. Now, this pipe has a head loss for 4 meters, right? This pipe 3 meters. You will find the head loss in each those pipes, okay? Each pipes. Now, if I used this pipe and this pipe, so it looked like I am going to find the head loss of those two lines together. How much it will be? It will be the head loss from A, B bar, right? So it will be 4 plus 3. How much it will be? It will be 7 meters. Am I right? Right?
Doctor, can you please repeat that?
Okay. After doing my calculation, there is a definition. It's called critical path. Critical path. We have the waters coming from this point to A2, and it's go through the network. It will go here, and it will go here, and it will go here, and there, and there, and there, right? So there is, for each pipe, this from A to D or D bar, there is a route. This is one of the routes, A, B, B bar, right? There is a route, we see that it's A, B, B bar. So we have the route A, B, B bar. What will be the route And the total head loss. The total head loss for ABB part, we have for AB, it's 4 meter, plus for BB bar, 3 meters, it's equal to 12 meters, 7 meters, right? Okay, now I will use another route. I will use another route. There will be another route. Here's the other route. Here's A, B, C, C bar, right? So we have another route which is A, B, B, C, C bar. Route A, B, C, C bar. And I will find the head loss through that route. The head loss through that route, it will be the head loss from A to B, which is equal to 4, right? Plus the route and the head loss from B to C, which I count. You have to find it again, but I have it in the lectures. Yeah, so from AB, from BC, here's the BC. What will be the head loss? BC, from B, it's 1.6. So there is a 1.6 meter. And we have from CC bar, here's from C bar, how much is the head loss? Is 1.3 meter. 1.3 meter. Now for that route, how much is the total head loss? It's equal to 4. And by the way, I don't know why we have in the lecture notes it's written 2. You have to check that one. It's equal to 4 plus 1.3 plus 1.6, 1.6, 1.3. Now, how much it will be the route? Total head loss in that route?
6.9.
6.9 meter. Right? And there is another route. Here's, let me say, there's another route. Here's another route. 1, 2, 3, 4. So we have A, B, C, D, D bar. We have A, B, C, D, D bar. And also you have to calculate AB 1.6 plus from PC 1.6. And we have from C to D and from DD bar. From CDD, from C to D, the 2.6, and from D bar is 2.3, 2.6 and 2.3.
Sir,
Yeah.
so according to what I understood is that even if we take different routes, we should get the same value or a close value? Or is it each route has its own?
So what I'm doing is I will find all possibles, all values for the all available routes, head losses, all the total head losses for each of the routes, and I will compare between them. And among those routes,
Should choose the smallest one, right?
Among all the routes, for example, the last route we have here is the last route. Among those 1, 2, 3, 4 routes, there will be 4 total head losses, right? The one that's giving you the highest value of the total head loss is called the critical path. The critical path or the critical route. Then what should we do? That route, it will give you the line that will happen in that network the most head losses. So what should you do? You should, first of all, for the next time, you should design that route first and go back to the laterals. This is called the main line. The idea is to find a critical path, and when you found that one, then all focuses will go through that path, and then this path should be designed very well, and the laterals will be. And by the way, the critical path, you can unify the diameter for the all pipes in that critical path to minimize the total head losses. And then there will be a branch. It look like what I'm doing. It look like I will convert the network to another network like this. All the pipes does. This is the main one, the main or the critical path, and then there will be branch. You know what I mean by this critical path. Here's the idea. So what you are doing, you will uniform all in one diameter will help you to minimize the total head losses in the all networks, because this is called the critical one, the one that will be affected on the network. Okay, so
Okay.
so you know why I'm doing this? I'm doing this to find all available total head losses in the network. And here is the all available head losses in the pipe. You can see for the pipe here, and by the way, I would say that I'm using 2 in, I don't know why it's 2. Just check that one. This is for ABB pipe. Will be the second. This will be the third. Will be the fourth. So you can see this one is the critical or the ultimate head loss. What is the ultimate? It's A, B, C, D, D bar. What is the A, B, C? A, B, C, D, D bar. A, B, C, D, D bar. So here's the A, B, C, D, D bar. So what you should do next, you can see we have different pipe diameters in. Here's we have 400. What you should do, you just unify all these yellow highlighted line with one line, and then the laterals, these are all called the laterals, will be using another pipe, and this will help you in minimizing all the head losses in the pipes. Okay, so careful, the critical path is here, the critical path, the pressure at D, and look at the D, the pressure at D will be the smallest of pressure, because we have, this is a critical path. And why, this is what the question is, they find the results from find, where is it? First of all, the minimum here is second is the different as in the form. Check the available pressure and specify the critical path. Now, this was one of the methods for analyzing, and we have the methods for the design of the water distribution networks. We have 4 methods. One of the methods that we have, this is for the few, usually will be used for few limited pipes. It's called equivalent pipe method. And this equivalent pipe methods, we have for the equivalent pipe method, we have few pipes. The pipes will be usually put it in this way. Either it will be put it in this way. For example, this is A, B, and this is C, D. So the pipe, we have A, we have B, and we have the pipe from A to B, pipe 1. We have the pipe from A to B, this is pipe 2. So pipe 1 and pipe 2 are connected together. In which method? In parallel. So we have, this is called parallel connection. The water is coming from this point and it will be distributed for A towards pipe 1 to B and it will be connected here. This is called parallel connection. Or we can have pipe 1, and we have another pipe, maybe pipe 2, and another pipe maybe. So the Q will become the pipes, the flow is coming this way, it will pass pipe 1 and it will pass pipe 2 and it will go on this way. This type of connection is called pipes in what? In series. So pipes in series are the pipes will be to link it in this way, and pipes in parallel will be linking in this way. What this requires from me? Sometimes you need to convert all these pipes to one pipe. So for each pipe, I have its length and its diameter, its length and its diameter, its length and its diameter. So what is required? It's required to just remove all of them, and I have to put one pipe instead of all of the three pipes. This pipe is called equivalent pipe. So equivalent pipe, it will be a pipe that will be sufficient to hold the same flow that this pipes are holding all of together. This pipe should have head loss equal to the same three pipes head loss together. So if I have 1 meter head loss here, 2 meter head loss here, 1 meter head loss here, and the total head losses of all the three pipes are coming to be 4, the new pipe, the new design pipe, the new equivalent pipe, it should be capable to hold the same flow with the same head losses for the three pipes. This is the method that we are using in having parallel pipe equivalent method. Is it that clear?
Yes, doctor.
Now, okay, so the flow will be go through this way and this way and this way. I have a pipe, another pipe, and the idea is to hold the same course. So this Q should be equal to the same Q. This is the equivalent pipe. And so the Q in the equivalent called Q equivalent, it will be equal to the Q of the above Q1 and Q2, Q3. So it will be equal to the same Q that will be for Q1, and which is equal to the same Q at Q2, and it's equal to the same Q of the Q3. The other thing that we have here, the head loss in this equivalent pipe, the head loss in the equivalent pipe, it should be equal to the whole head losses in the pipe here. So head loss in pipe 1, head loss in pipe 2, and head loss in pipe 3. So the head loss for the equivalent pipe whole should be equal to here 1 and head loss pipe 2 and head loss pipe 3. This is just in case we have a series pipe connection. What will be if I have a parallel one? This is the parallel one. So the parallel one, this is the parallel, and if I want just to remove all these pipes together and put only one pipe here to this one, equivalent one. So the Q here in this equivalent pipe, Q equivalent, it will be equal to Q in pipe 1 plus Q in pipe 2 plus Q in pipe 3. So this new pipe, which should be equivalent to the old pipe 1, 2, 3 together, they should have the same, they should hold the same Q. Now what we have here in the series, in the parallel pipes, the difference between the head loss between this point A, for example, B, the head loss from A to B, it will be equal to the head loss of pipe 1, it will be equal to the head loss in pipe 2, and it will be equal to the head loss in pipe 3. So the head loss here is equal to the head loss in pipe 2, and it will be equal to the head loss for equivalent pipe. So equivalent pipe is equal to the head loss of the pipe 1 and head loss of pipe 2 and equal to head loss pipe 3. Unlike the series, in the series we will add all the head losses together to get one head loss, and we say this is will be for equivalent pipe. Now we have for the parallel one, we will use this method, and it's somehow look like the electricity. The voltage difference in voltage between A and B will be the same loop A and B has. Now, what we
Yes,
should,
circuits.
yeah, circuits, yeah, so thank you. Now, if we go to this pipe, for example, this example, we are using William Hazen nomograph. By the way, this is the HOMO nomograph. You have to check that this can be used for C equal to 100. We say that we have two equations for calculating the head loss in the pipes. Either it will be William Hazen or it will be Darcy-Weisbach, and you can use any of them based on the Darcy-Weisbach. It will be somehow difficult to use in the pipes. Now, this is what the question, find an equivalent pipe for this one. When I say that find equivalent pipe, I mean by this one, find the length. Because you know that the length of this pipe is equal to how much? So I want to just remove that one. I want just to remove that all the three pipes, and I will have to put another one equivalent pipe to substitute these all three pipes. What should I do? This is, by the way, the equation of the William Hazen after some modification. You can use this one or you can use this one. But if you have a C equal to 100, it will be easiest to use the nomograph. If you don't have that C, you just use the equation, that's it. What I will do, I should, if its Q is not given, if Q is not given to you in this pipe in series, so you should assume a value of Q. And the assumption will be either 50 or 100 liter per second. So this will be used for the assumption. What I will do, the procedure is that I'm looking for a pipe. This is the equivalent pipe. This will be a pipe that will be equivalent to this one, equivalent pipe. But for this equivalent pipe, I don't know its length or diameter. You have to assume one of the diameters and find the length, or you have to assume the length and find the equivalent diameter. So first of all, you have to assume a Q. And then from that Q, for pipe 1, we have the flow, we have the length, we have the diameter. What's missing? I will find the head loss in pipe 1 by using either this or either this one. So for pipe 1, when we have a Q of 100, the diameter is 400 millimeters. I have to go with this one, 100 by 400. Where is the 100 millimeters? 100, the flow, liter per second, here is liter per second. So this is the 200, this is the 100. And I will use this 100. And where's the diameters? The diameter is 400, right? This is the 400. 400 means 40 centimeter, right? This is the 400. The pipe diameter in centimeters. Centimeters, 40 centimeters. It means 400 millimeters, which is in the equation for it. Now, what I should do, I should just connect between these two points together and see how much it will be the rest. Now, I get the value of two things. What are those two things? I will get the value of, will be what?
S and H.
Yeah, very good. So this is the velocity and this is the S, and I mean, I want to see how much will be kilopascal per 100 meter, or it will be, look at this one, it will be head losses in meters of water per 1,000 meters of the lake. So this is meter per 1,000 meter. Means this value is 2.5. It's look like to be 2.25, right? It's 2.3 times 10 to the power minus 3, because it say that it's meter per 1,000 meter. And meter per meter, right? It's 2.3 meter per 1,000 meter, which is equal to 2.3 times 10 to the power minus 3 without units. This will be the S, or the head loss per length, right? So I will find for this pipe the S, which is 2.3, and this is 2.3, or 2.3 times 10 to the power minus 3. Now I have the length of this pipe. The length of this pipe is 1,000. So how much? By the way, you can see we have me and the answer. It will be somehow different from person to another person. It's all depend on the accuracy. 2.3 times 10 to the power minus 3 times the length, because this S is HL over L. Now I have the L of this pipe. So the L is 1,000. So how much it will be the head loss for pipe 1 is 2.6. Now we have 2.6 the same way for pipe number 2. I have 100, I have 350. Where's the 350? This is 400, there is 500, this is 350, and I will connect to see what will be the so how much it will be the value of S for the second thing. It will be around, will be the value of S, it will be 1, 1.1, 1.2, 1.3. Am I right? It's 1.3 times 10 to the power minus 3. So oh, it's too much. We have too much difference. 315. Oh, the diameter is wrong.
Doctor, that diameter is not correct.
Yeah, was the wrong thing.
Yeah.
Where's the 315? This is 500. This is 300, 310, 20, 30, 40. This is the 350, by the way. Because, so what should I do? I will just connect between this one. Now we have 310, 20, 30, 40, 50. Yeah. So how much it will be the S? It will be 50, 40, 45, 45. Yeah. It's about 4.5 times 10 to the power minus 3. Again, there is somehow differences. So we have 45 times 10 to the power minus 3. And the length of this pipe is 650. So how much it will be the length? the head loss, just multiply this one by this one. You will get the value of H2 and H3. Adding all of them together, we will get the total head. The total head is will be 10 to the power 86. Now, for the new one, for the equivalent pipe, what should I do? I have the head loss, the 10.485 meters. That's the whole head loss. Head loss is equal to 10.85. Now I should find the S because I don't have neither its length nor its diameter. Let's say I will pick a diameter for the new pipe in between. It's not be 400, it will not be 300, I will take it as a 350, or any pipe diameters you like. For my case, I will assume for the new pipe, let me say I will unify all of the pipes together. I will use 355 millimeters. This is the diameter of equivalent pipe diameter. So I have the diameter is equal to 3.50 millimeters. What left for me? I have the Q. The Q is equal to the whole Q of this pipe. Where's the whole Q? The whole Q is the 100. I assume that the whole Q is 100. So I have this 100 and I have the diameter. When you have the Q of 100 liter per second and I have the diameter, so what I should find, here's the 100 and here's the 350. You will see the pipe, the HL for the new equivalent pipe, S equivalent pipe is equal to 4.5 10 times to the power minus 3, which is equal to the head loss divided by the length. The head loss of the whole pipes was 10.85. Now this is the equivalent length of the pipe. So now I think you know what we did. We first of all we found the head losses on all the three pipes that I had. Yeah, I add them together and I found them. They were 10.3. For the new pipe, I assume that the equivalent pipe is equal to 350 millimeters. Now the whole length, the whole head losses here is 10.8. I have the diameter. Q, I will find the S. After finding the S, this S will be equal to the head losses that we have 10.85. Now divided by the length of the equivalent pipe, which as I'm looking for. Or you can do another thing. You can assume the length, add all the lengths together to find a diameter for the new pipe. You can do that, but usually we will have an information about the pipe diameters that we have to use it previously. This way, we will find the length of the pipe diameter, which is equal to 2,370 meters. Yeah.
How did you get that S equivalent at first, after assuming the diameter equivalent to be 350 and the Q to be 100?
Yeah, so what should they do? I will go back to the same nomograph and I will 100, 350, I will find the S. The S for this equivalent pipe. Now, after having this S, I have the head losses of the whole equivalent pipe, which is equal to the 10.85 meter. Now, I have this one from nomograph. I have this one from the previous, those three pipes. So what I should find the equivalent pipe length for the whole three pipes. Or you can assume a length of the pipe. For example, if I want to exchange all those three pipes, how many the length of the pipes that we have? I have 1,650. For example, that's 1,650 plus 500. That's 2,150, right? 2,150 meters. This is the whole pipe length. If you want to, for example, you do like this. You want to just add more pipe lengths to pipe. For example, if I want a new pipe to be its length as 2,500 meter, but I don't know what's the diameter. That means you assume the length of the equivalent pipe equal to 2,500. You have the head losses, how much it should be. It will be 10 to 10.85 meter, 10.85 meter. So you have 10.85 meter the head loss, and you have the length, then I will get the S. Now, if you have the S and you have the flow, then you connect between them and you will get the best fit diameter for that equivalent pipe. Here's the method. Or you can what? You can add, you can assume a diameter. For example, you have to unify the diameters, but it will take another length. You have to have another length. You say that instead of 2,115 meters, you will get 2,370 meters length. So you have to make a sag diagram, or you have a pipe. You are not taking in serious what will be the start and what will be the end point. Okay, this is in case that we have pipes in a series. Next lecture, I will tell you how to do the pipes in parallel and also to do another pipe. Got this one, for this example, it will be more easier. We have a pipe. This is a pipe. This is A, and this is B. You say that the ground level of A is 10 meters. What is that means? That means this is the datum. The ground level of the pipe at A is 10 meters. And the ground level of B is 20, sorry. Means the pipe is going up. The ground level of B is 20. This is pipe, this is B. The ground level, this is the ground level. And this is the ground level of B is equal to 20 meters, and the point A, the ground level at A is equal to 10 meters. Now we have the head loss of water in pipe in A is 5.5, and in B is the head at B is 20. Means that the water in this pipe have a pressure of 20 meters, and the pressure at this point is 5 meters. Means that the water is coming from B and going to this is the hydraulic gradient line. Hydraulic gradient line elevation. The pressure at the head at B is equal to 20. The head at A is equal to 5. Means what? Means the water is coming from B and it's going towards it will go from the high level to pressure to low pressure. So the flow is, the Q is from B to A. Now, how much is the head loss? So the head loss from B to A, it is the total head of B minus the total head of A. You remember that from the fluid mechanics, the head is equal to the pressure plus the ground level. Now, we have the ground level of B is 20 meters. And the pressure at B, it's 20 bar, not 20 meters. I think it's 20, yeah, it's 20 meters, yeah. So 20, so the level at, I'm sorry, there is a trick here in this question. It's a bar, and bar is equal 10 meters. So it means the head at point A is equal to 5 times 10, it means 55 meters. Okay, and then it means that the water is going from A to B, not from, it's upside down. So even the ground level,
the next class.
yeah. So even the level at A is lower than B because the ground level is here is 10. This is B, but the pressure at A is 55. The pressure at A is 55 meter, while the pressure at B is how much? 20 meter. So the water is going from high pressure to low pressure. This is will be the S and the flow. So the head loss from A to B is equal to the pressure at A, total head at A minus total head at B. How much is the total head at A? It's 55. This is only the pressure you have at that 10 meter, because the total head is equal to elevation head plus the pressure. So 10 plus 55 is equal to 65 meter. This is will be the head at the head, where is it? Yeah, the head, total head is equal to 60 meter at A minus. The level of B is 20 meter, pressure at B is 420, so the total head at B is equal to how much? It's equal to 40, because 20 plus 20. So what will be the head loss? This is will be the head loss from A to B. It's equal to 16 minus 40, it's 16 meter. This is the head loss. Divided by the length, let me say, how much is the length from A to B? It's 2 kilometers. This pipe is length is equal to 2,000 meters. Now, can you tell me how much it will be the value of S? The value of S is equal to head loss divided by length. The head loss is 16 meters divided by the length, which is 2,000 meters. And it will be 16 divided by 2, it's 8 times 10 to the power minus 3 meter to meter. Now, you have the S and you have the diameter. It's equal to 300 millimeter. What is required? It's required to find the discharge, the Q. So what I will do, I have those two ones. I will use either the nomograph if the value of C was 100, or use the equation if the value of C is not 100. Now you can see that C is not 100. So what I will do, use the equation. The equation, here's the equation. This is the equation. Yeah. So the equation is say that the head loss HF divided by the length. What was the HF? HF over L, here's the HF over L is 16 by 2000. So 16 divided by 2000 is equal to HF over L. That is equal to 10.67 divided by C. The value of C is 140. This is 140. Power how much? 1.85 times. What will be the diameter? That's what I'm looking for. I can't find it. And what will be the value of D? The value of D is equal to 0.3. Remember that all the dimension should be in meter. This is will be 0.3. Power 4.87. Now this is the equation. You have one equation with one unknown. You can find the Q. Then I can say Q is equal to 16 divided by 2000 times 140 power 1.85 divided by 10.67 times 0.3 power 4.87. So Q power 1.85 is equal to 0.0198. Now, what I will do, I will reverse, I will say power 1 divided by 1.85. So the Q will be equal to 0.1203 meter cube per second. This is the flow. So the flow in this part will be equal to this much. Okay. In case that you don't have this value of C, you can use easily this number. Guys, do you have any question?
No,